Hello everyone. In this video, we'll cover the assigned reading for this week, uh, where we are going to cover topics of relational database design and normalization. So specifically, the topics we cover are what makes a schema good, and we'll talk about briefly talk about functional dependencies, and then we'll cover these in more detail in the class. So the relational database design, the question that we're trying to ask is, why did we use that specific schema? Was it actually a good schema to use? Why not store the student names with the takes relation? What would be the problems with that? If we designed the schema using an ER diagram, then a related question is whether we made the right decisions with the ER diagram. So in other words, our goals are to formally define what it means for a schema to be good and how to achieve it. Okay, so we'll start with some of the requirements for a good schema. Talk about what makes a schema good versus not good. We'll use the movies database schema for this purpose. Take a minute to look at this. Here we have a movie table with title year as the primary key, and we have some other information. The movie star has name as the primary key. Movie executive has a certificate number as a primary key and has other information like name, address, and net worth. And studio has a name as a primary key. Okay. And one thing we're going to do here is that, so this is our original schema that we had. We're going to combine the movie and stars into a single relation. So we have the title, year, length, in color, studio name, producer, certificate number, and star name. So we have essentially merged these two. And now the question is that a good decision or not? And more specifically, why is it not a good decision? So if you look at an example schema, example relation for that schema, title, year, and all the way to star name, note that this schema now has title, year, comma, star name as a primary key. This is because for different actors, we need to have different tuples. So in Star Wars 77, we have the rest of the information, and then we have the actor name. Star Wars 77 actor name, Star Wars 77 actor name. And so clearly Star Wars 77 is not a unique anymore, so the title year cannot be a primary key. So the primary key is Star Wars title, year, and star name. And this immediately makes it clear what the problem is. We have a huge duplication here. All these four columns are duplicated in every row with the same title year. And clearly such duplication should be avoided. There are several reasons for it. First of all, of course, it requires higher storage, although we don't really care about storage nearly that much. The bigger concern is potential for inconsistencies. It's possible that user might update the studio name for one tuple and may forget to update it for the other tuples. Or we might insert a new tuple for Star Wars 77 with another actor, and we might have a wrong information for the length. Okay, this cannot happen in the original schema. In the original schema, the length of a movie was only stored once, so it's not possible for there to be a duplication or inconsistency. In this case, because the attribute is duplicated, we have potential for inconsistencies, which is because of the schema. Okay. You also need to use nulls to represent some tuples. So for instance, if you have an actor, if you have a movie without any actors, then the only way we can store it is by using a null in the star name. And that obviously again is undesirable. One option that you might think of is that why not make star names a list attribute? So we have the rest of the information for the movie as is, and then we have an array or a list with all the star names in it. But arrays are undesirable for a variety of reasons, and in fact we prefer to avoid arrays or lists as much as possible. They are hard to represent and they are hard to query. In terms of representation, storage layer gets complicated if we need to reason about arrays because they are variable length, and they are hard to query because the query languages that we've talked about, SQL, relational algebra, they don't allow you to look inside the attribute, and it becomes a little bit tricky. For instance, how do I do a join between this and the movie actors table? Now the join is on the name here and the name in the movie actors table, and that there is no easy way to do that. Now, you might think that smaller schemas are always good, but that's also not necessary. So let's take the studio relation. We have three attributes: name, address, and precedent certificate number. Name is a primary key. So we can imagine splitting this up into two relations. Studio name, studio one name, precedent certificate number, and name address. Now this what is called a decomposition. This decomposition is fine. It's not a problem, except that it requires more joins, and there are no obvious benefits. We don't really save any space because we're still going to have the same number of tuples and same amount of bytes required to store them. And some sort of dependencies can be hard to check, like a dependency between uh, precedent certificate number and address can be hard to check if we split them across two tables. Decomposition can also be problematic in that it can lead to loss of information. So here is an example. We have the stars in table with movie title, movie year, and star name, and we decompose it into movie title, movie year, and movie title, star name. There's obviously a problem. There's actually an incorrect decomposition, because if I join these two relations, I get more tuples back than I started with. This is because this movie title King Kong here matches with this movie title King Kong, even though this particular record uh, should only match with the 2005 movie, not the 1933 movie. But we have lost that information. We have lost the information that this 1933 and this phi are the same tuple, this 2005 and this watts are the same tuple. And because we have lost this information, this is called a lossy decomposition. And lossy decompositions are not just a performance problem, they're just wrong because we are representing wrong information at this point. Okay. So some desired properties that we want from our schemas, we don't want sets. Sets are problematic. We want the design that we have, the schema that we have, to be faithful to the original design, and in particular, we need to avoid lossy decomposition. We want as little redundancy as possible. There should be no need to use nulls to store information as much as possible. And finally, a subtle point of dependency preservation, which is that it should be possible for us to check for constraints in the data. It turns out that all of these are not possible to guarantee in the same schema, as we'll see later. And otherwise also, we sometimes relax these for simpler schemas and for avoiding joins during queries. So in fact, we sometimes compromise on the redundancy criteria so that the query performance is better. Okay, so what is our approach? So roughly speaking, our approach is that we're going to encode our knowledge about schemas in the form of what are called functional dependencies and later on what are called multi-valued dependencies. Then we will define a set of rules that a schema must follow to be considered good. And specifically, we'll call those normal forms. So a normal form, this is where the normalization term comes from. A normal form specifies constraints on the schemas and the functional dependencies. And if a schema is not in a normal form, then we modify the schema. The way we represent our knowledge about the schema is through what are called functional dependencies. So this is an example of functional dependency. SSN implies name. What this basically says is that if two tuples have the same SSN, they must have the same name. Okay, and we'll see some examples of functional dependencies in a couple of slides. For instance, movie title implies length is not true. So if you go back to this relation that we had, movie title, we have two tuples with the same movie title, but their length is different. So movie title implies length is not a functional dependency. On the other hand, movie title, movie year implies length is a functional dependency. There are many different normal forms, starting from first normal form, second, third, BCNF, and fourth. The ones we'll focus on primarily is the Boyce Codd normal form. There is a stricter and stricter normal forms in that a schema might be in 1NF but might not be in 2NF, and so on, but the other way is not possible. So a schema that is in BCNF is also in 3NF. Schema that is in 3NF is also in 2NF. We won't really talk about 2NF, and we'll briefly discuss 4NF at the end. Okay. Basics of functional dependency. So let's define it a little more formally. Let R be a relation schema, which means let R be a list of attributes in the relation. Alpha and beta represent sets of attributes. Okay, not just one attribute, but sets of attributes. And then we say that alpha implies beta is a functional dependency for R if for any legal relation, if two tuples T1 and T2 of R have the same value of alpha, they have the same value of beta. So in this case, we write it as T1 alpha equal to T2 alpha implies that T1 beta equal to T2 beta. Okay. In other words, two relations have the same value of alpha. They have the two tuples have the same values for alpha. They have the same values for beta. Okay. Here is an example. We have a relation with two attributes, and here we see that A implies beta is definitely not true because there are two tuples with same value of A but different values of B. But B implies A does hold on this particular instance, in that for there are no two tuples with the same value of B, so it's sort of trivially true. However, this does not necessarily mean that the B implies A is a functional dependency, because do we know for sure that there is no other tuple that is going to be inserted which might violate the constraint? What if we have a tuple that is 2 comma 4 that comes in later? If a tuple 2 comma 4 comes in later, then suddenly B implies A is not true anymore. So in order to reason about functional dependencies, we have to think about the domain and the possible relation instances, not just a given relation instance. Okay. So again, this thing makes the same point. Here, for instance, with these four tuples, we can see that title implies year is actually true. In this case, two tuples that hold the same value of title have the same value of year. But clearly, we know that this is not true. Title does not imply year. When we have two movies can have the same title but could be in different years, and so there is not a true functional dependencies. So in other words, we have to think about the all possible legal relations, which of course means that we need to understand the domain to be able to talk about functional dependencies. Uh, so here's another relation where I've combined a bunch of information across several different relations in our movie schema. And so the question is, what are the functional dependencies here? So this is a little bit tricky. You have to think about it carefully. For instance, um, two tuples that have the same producer number are going to have the same producer address and same producer name. This is because the producer number is producer certificate number is unique across the producers. So one functional dependency that holds here is that the producer certificate number implies producer address. Okay, because two tuples that have the same producer number will have the same address, and same goes with the net worth. So in fact, we have several functional dependencies here. Producer certificate number implies producer address, producer certificate number implies producer name, producer certificate number implies net worth. Aside from that, we have the title year implies length. Remember that we assume that a movie is uniquely defined if we know its title and the year. So title year implies length is another functional dependency. Star name implies birth date is another functional dependency, because again we are assuming that star names are unique, so they uniquely define the birth date. Okay. Here's another schema, and I'll let you think about the functional dependencies in this schema. So there's different functional dependencies here are that course ID implies title, department name, credits, building room number implies capacity, and so on. So what is the problem with the functional dependencies, and why do we want to think about them? So consider a table R, A, B, C, okay, with a relation R with three attributes. And let's say that we have functional dependencies that B implies C and A implies BC. Okay, note that A implies BC is equivalent to saying that A is a primary key or A is a candidate key, because this will guarantee that A has to be unique. Okay, but B is not a key. Okay, so A is a key, but B is not a key because we might have duplicated values of B as shown here. Okay. So what's happening here is that there is a functional dependency. There is a functional dependency, B implies C, such that its left hand side is not a key. And that's where the problem comes. That's where the redundancy comes. So here is an example relation. We have A is unique because A is is a key for this relation. B is not unique, but this relation does satisfy the functional dependencies. Clearly, A implies BC is true trivially because A is not duplicated, but you can see that B implies C is also true. We have three tuples with the same value of B; they all have the same value of C. Same with B, these two tuples and these two tuples, and B3 and B4 are not duplicated, so they also satisfy the condition. However, because B implies C, what this means is that anytime B is duplicated, C is going to be duplicated. Okay, and that's where the redundancy comes from. So the way we can get rid of this redundancy is by splitting the relation into two relations. We create one relation with A and B and the other relation with B and C. Now you don't have that problem because in this relation B1 is duplicated, but there is no C here, so that B is duplicated, but there is no C here, so that's not a problem. And here B cannot be duplicated, so there is no question of C being duplicated. Okay. Note that this here, this is not a redundancy. Okay. We just happen to have three different A's that have the same value of B. That's not a redundancy. This is redundant information because we already know that B implies C, which means that if we know the value of B for a tuple, we know the value of C. So there is no reason for us to store it multiple times, which is what's happening here and here. Okay, and that redundancy goes away once we come to this. Okay, one thing I want to say, I don't have it on the slides, is that, but I have it on the reading homework, is that a notion of a trivial functional dependency. So a dependency is called trivial if its left-hand side, so going back here, its right-hand side is completely contained within its left-hand side. So for instance, A implies A or AB implies B. All of these are trivial because they're trivially true. In that if a tuple has the same value of A, of course it has the same value of A. If tuple has the same values for A and B, it will have the same values for B. And that's why those are called trivial functional dependencies. Finally, Boyce-Codd normal form. We call a relation schema is in the Boyce-Codd normal form if for every functional dependency, either the dependency is trivial, that is B is contained in A, or A is a superkey of R. Okay, and this again shows a similar example as the previous example, where we see that as long as we don't have a situation where the left-hand side is not a key, we avoid redundancy. Okay. So this is just a brief overview of some of the early topics on the reading homework. We'll talk about different types of normal forms, how to achieve them, and go over some examples in the class.